here's the big conceptual overview thing. Whenever something has a net acceleration, so if you're told that, such and such undergoes a net acceleration of 10 meters per second squared, 500 meters per second squared, whatever, the net force on the object, or the person, or whatever, is equal to the mass times the net acceleration. Okay? So conceptually, that's where each of these problems is starting. That the net force on the thing is equal to the mass times the net acceleration. Now, you've done net force in the 4A stuff. That was all about finding net force, finding net force, finding net force. So you know that you can have a bunch of different forces going into net force. And that the net force, if we think back to the kind of stuff we did in the last section, the net force is equal to, very often, like if we're dealing with just the y-axis, the force up and the force plus the force down. Well, in the last section, in the last set of problems, we were dealing with cases where this net force was 0 because the thing was not accelerating. It was either standing still or it was at constant velocity. And since now we're dealing with things where there is actually a non-zero net acceleration, what we're starting to do with all of these is say, well, the net force on whatever is equal to its mass times its net acceleration. And that mass times net acceleration is equal to all the forces on it. And so very often, and I'm simplifying here, that's going to be the total of the forces up on it and the forces down on it. If we're dealing with something that's accelerating on the y-axis. If we're dealing with something accelerating on the x-axis, it's going to be, the forces left and right, the forces east and west, whatever our axis is where the net force is existing. So then what we end up with is this chunk. So we can identify all the forces acting on it. And these are cases where you either have a way to identify all the forces and you get either the mass or acceleration you're finding for one, or more commonly, you have the mass, you have the net acceleration, and you're attempting to find one of the forces that's acting on an object. Okay? So with that sort of conceptual overview, let's go back to Bob and do this right this time. No, this is Bob. This is number 5.
No, that's a person.
That's a person. It's only got 4 legs. If it was ClickBeetle, it'd have 6. So anyway, we've got Bob hitting the ground, and we are told what Bob's net acceleration is. So here's what we know. The net force on Bob is equal to Bob's mass times Bob's net acceleration. And we know that that whole thing is equal to all the forces acting up on Bob plus all the forces acting down on Bob. Okay? Conceptually, this is good so far, right? Okay. True statements. So we can scrap that. And there's the part we're working with. So we know that Bob's mass times his net acceleration is equal to forces up plus forces down. What force is acting up on Bob?
No.
Well, it's just the force of the ground in general acting upward on Bob. So I'm going to call it, because force ground is a lot like F of G. Well, what I was going to use is collision,
Oh, that works.
because force field doesn't. That has other connotations as well. So the force of the collision with the ground is the force upward on him. And adding to that is the force of gravity acting on him. So the force of gravity acting on him is equal to what? And that's of course down. It's equal to what? mg. M times g. And of course, these are in opposition one of these is going to be a negative number, and if we use negative 9.81 meters per second squared, and I'm going to keep these in here for myself, then that'll work. So we can do a little bit of algebra here. M times the net acceleration, which we're given, minus mg is equal to the force of the collision on him. Okay? Does that make sense conceptually? Okay. Now, the place where you have to watch your sign stuff and where the book handles it differently, obviously, the force that the ground is exerting up on him has to be greater than gravity. Gravity is adding to whatever additional force there is. But if this is, so we can even factor out the mass, A net minus G. Remember that that's a negative number.
Do we usually factor that out?
It's often useful to do that, yes. It is often, especially as we get into later problems where there are some additional complexities, it's very helpful to be able to factor out that mass. Okay, because what we know to be true is that if that's the magnitude of the force of gravity, the force of the collision has to, I mean, just him laying on the ground like a slug, the ground's exerting that much force up on him. The force of the collision increases the force, and so that's where you've got that additional piece. Okay, so we can now plug in some numbers.
And that means upward and downward.
There's the force of gravity on him. If he was just laying there flat on the ground would be exerting an equal amount of force to gravity. But since the ground is stopping his motion, it's accelerating him upward, it's exerting more than the force of gravity on him. So yes, you are adding the force of gravity to his upward acceleration. Okay, so what do we get for our raw? Okay, so for a raw number we get 18,658.2 newtons is the force of the collision. What do we have? 3 sig figs? Yeah. So in round figures, 18,700 newtons upward is the force of the collision. Okay. Does that feel better conceptually? Breaking it down that way? We're going to keep doing these together. So we've got a very large toad in this weird apparatus. It's on like a little toad elevator suspended on 2 cables. And we're given the toad's mass, we're given the force of gravity on the toad, and we're given the net acceleration. So the toad is being pulled upward on this little cable contraption. And what we want to know is the force of tension in each of the cables. So, what we're going to start off with, let's first just deal with our x-axis and then set it aside. So, sum of forces on the x equals 0, right? Because it's not moving laterally. There's no side-to-side motion here. And what are the forces that exist on the y-axis? Or x. What are the forces? Right. Ft1 on the x and F of T2 on the x. They're in opposite directions. They equal 0. We know they have to be equal and opposite. We know that. We've made a note of it, and now we can set it aside and forget about it. And I will actually set it aside right up there.
So is this like the other ones we did?
Well, no. It's an accelerate. It's a problem with non-zero acceleration. But on the x-axis, there isn't any acceleration. But we're just setting that aside. In this one, it's not useful, but in some of them, like in the one with the multiple cable angles, you need that other axis. Okay. Now, we know that all of our net force, where all of our motion is happening, is on the y-axis. So our net force on this thing is basically going to be the sum of the forces on the y-axis. And our net force is equal to its mass times net acceleration and it's also equal to what? Yep, F up and F down.
That actually makes a lot more sense, so rather than just skipping that part.
Yeah.
saying the up and down.
It does, it does. Yeah, and it might feel a little bit juvenile to some people, like, well, I know it's the force of gravity and the force of... But it's, I find it to be a helpful sort of mental bookkeeping thing. Okay, so now we have the chunk we're going to deal with. So mass times net acceleration. What are the forces up here? Pardon?
Force it down.
Force up?
Wait,
Let's go with our forces up first.
okay. No.
Well, we don't really have normal force here. We're looking at the force. Yeah, it's the force of tension. So that the pressure that the plate is exerting upward on him is really, it's tension from the cables. So we have F of T1 on the Y plus F of T2 on the Y plus, what's our force downward? Gravity. Gravity holds things to the earth, you see. All right. Now, we know that those two are up and that one's down. We're given mass, we're given net acceleration. Now, what expression can we use to describe that force of tension on the y-axis? Looking at our triangle here.
What?
Okay, looking, what expression would mathematically describe our force of tension 1 on the y-axis?
13 sine, or sine 45.
Yeah, so force of tension times the sine of 45. Or, I'm just going to, for now, I'm just going to say sine of theta. And for the other one, it would be force of tension 2 times sine of 45.
Wait, I was saying theta or 45.
Oh, shoot, sorry. Jeez, oh, Pizzo Moser. Get it together.
So the FT1, the sine of theta, theta 1. We know it's-
Yeah, but we know that they're the same angle. So, we know that theta 1 equals theta 2, f of t1 equals ft2. All right, so now we can take our next step, because we know that f of t1 is equal to f of t2 and theta 1 is equal to theta 2, we can say the mass times the net acceleration is equal to 2 times f of t sine of theta, because they're the same, plus f of g. How many of you can suddenly see where this is going? You can see how you're going to solve algebraically for this. Yes? We're looking for the force of tension. Yes. In each case. Okay.
It's probably
Moving on to the next step. All right. So mass times net acceleration is equal to 2 ft sine theta plus, what's another expression for fg? Mass gravity.
Doesn't it give it to us?
It does. It does. But if we have an expression, we can do other things with it.
So don't use triangles.
I would use mass gravity.
Okay.
Let's shrink some of this. Okay. So now we can start doing algebra. We have f of t as an actual variable that we can isolate. So mass times net acceleration minus mass times gravity equals 2 f of t sine theta.
So you just divide.
Are we taking that?
So now you can factor out mass if you want.
Is that the trick?
That's the trick. And it's one of those where we don't need to do it in this, but it's a practice thing. Because you come to a lot where you have to start finding mass, and if you can factor out that mass, then you've got it isolated. So, and now it's just pure algebra. So we'll plug in. Okay, we've got some numbers in there. We're ready for a raw number. Does that look like the raw number you have?
That was two but
You have what?
two at the last number.
Oh, that's because you have one less or one more space on your calculator. They're just handling rounding differently, I would imagine. So, okay, so we have 23.16, etc. newtons, and how many sig figs do we have? 2. So final answer, 23 newtons is equal to the force of tension in the cable.
So if they give us a picture and the 45 degrees isn't in like the problem that it tells us, but it's in the picture it gives us, then we do give it for
Well, oh, you're right. You know what? We could have had 3 sig figs. You're right. Now, see, if we had used the 26 newtons, we wouldn't have had 3 sig figs. We would have only had 2. You're right. That should be 23.2 newtons.
So if they give us something in a picture, we don't use it, it just has to be.
No, or maybe, yeah, you should. You should, because it's a given measurement that you're using.
So it's
2.
please tell me you're recording.
I am. 23 newtons, force of tension. As I said, what's better than screwing something up? For your physics kids, screwing it up, recording it, and putting it on YouTube. Woohoo! My mistakes will live in infamy.
What are those people that watch it?
Start number 9. What we have is a wire that is supporting a person. So this wire is exerting a force upward on this person. This is force of tension. Or a load, an object of some sort. It barely supports the weight of a 70-kilogram person, we're told. The wire is being used to lift a 45-kilogram object or person or whatever, 45.0 kilograms. What's the maximum upward acceleration that we can get that will not break the wire before it breaks? So what we have to know first is the force at which it's going to break. So the force at which it will break is equal to the mass of a 70-kilogram person times gravity. Because it can just hold the 70-kilogram person. You can't move them up or down. So maximum braking force is 70.0 kilograms times negative 9.81 meters per second squared. That's your brake force. So what we want to know is what net acceleration can we achieve? Because that's our maximum allowable, I guess I should have called that, the maximum allowable force on this thing.
So when we do that, we just make that like a positive number,
It would, yeah, because it would actually be upward, so it's in opposition to that. We will finish this tomorrow.